Guidance for inspectors, on-stream and off-stream boiler inspection based on API 510, API 572, and ASME, best practices for safe and effective boiler inspections. Please note that this presentation reflects the presenter's perspective only. Introduction and purpose of boiler inspection guidance, overview of applicable codes and standards, boiler types and major components, on-stream versus off-stream inspection philosophy, regulatory and jurisdictional considerations, API 510 scope and application to boilers, API 572 general inspection practices, ASME code considerations for in-service inspection. Common boiler damage mechanisms, fireside and waterside corrosion mechanisms, cracking mechanisms in boilers, creep in overheating. Damage, objectives of on-stream boiler inspection, on-stream inspection techniques, on-stream visual inspection checklist, on-stream NDE methods for boilers, objectives of off-stream boiler inspection. Off-stream inspection techniques, off-stream visual inspection checklist, off-stream NDE coverage and planning, inspection of boiler shells, inspection of tubes and tube sheets, inspection of headers and drums, inspection of welds and attachments, inspection of refractory and insulation, thickness measurement requirements, corrosion rate and remaining life assessment, minimum required thickness evaluation, fitness for service considerations, inspection planning and interval determination, risk. Based inspection application, inspection documentation and reporting, common boiler inspection findings, safety precautions during inspection, inspector qualification and competency, shutdown preparation for off-stream inspection. Final recommendations and follow-up actions. This presentation provides structured guidance for inspectors responsible for evaluating the mechanical integrity of boilers during both on-stream and off-stream conditions. Boilers are critical pressure-retaining equipment, and their failure can result in severe safety, environmental, and operational consequences. The purpose of this guidance is to align inspection activities with internationally recognized standards, specifically API 510 for pressure vessel inspection, API 572 for inspection practices, and applicable sections of the ASME boiler and pressure vessel code. The presentation is intended to support inspectors in understanding inspection objectives, identifying damage mechanisms, selecting appropriate inspection techniques, and documenting findings in a consistent and technically sound manner. Emphasis is placed on differentiating between inspections conducted while the boiler remains in operation, on-stream, and those conducted during shutdowns, off-stream, as each approach has unique limitations, risks, and benefits. By following this guidance, inspectors can improve inspection effectiveness, ensure regulatory compliance, and support safe and reliable boiler operation throughout its service life. Boiler inspection activities are governed by a combination of design codes and in-service inspection standards. API 510 establishes requirements for the inspection, rating, repair, and alteration of pressure vessels, including certain boilers not fully covered by jurisdictional rules. API 572 provides practical guidance on inspection techniques, damage mechanisms, and evaluation methods that support API 510 implementation. The ASME Boiler and Pressure Vessel Code, particularly sections I, 4, and 7, defines original construction rules, allowable stresses, and recommended inspection practices. Inspectors must understand how these documents interact, as API standards generally apply to in-service conditions while ASME governs design and construction intent. Proper application of these codes ensures that inspection decisions are technically justified, legally defensible, and aligned with industry best practices. This overview establishes the regulatory framework used throughout the remainder of the presentation. Understanding boiler types and their major components is essential for effective inspection planning and execution. Common boiler types include fire tube boilers, water tube boilers, and waste heat boilers, each with distinct design features and risk profiles. Major components typically include drums, shells, headers, tubes, tube sheets, nozzles, weld seams, supports, and refractory or insulation systems. Inspectors must recognize how pressure, temperature, and flow conditions vary across these components, as these factors directly influence damage mechanisms and inspection priorities. Familiarity with boiler configuration allows inspectors to focus attention on high-risk areas, select suitable inspection techniques, and interpret findings accurately. This foundational knowledge supports both on-stream monitoring and detailed off-stream internal inspections. On-stream and off-stream inspections serve complementary roles in a comprehensive boiler integrity management program. On-stream inspections are performed while the boiler is operating and are primarily intended to monitor known or anticipated damage, verify operating conditions, and detect early signs of deterioration without interrupting production. Off-stream inspections are conducted during planned shutdowns and allow for more extensive visual examination, internal access, and comprehensive non-destructive examination. Inspectors must understand the strengths and limitations of each approach, including access constraints, safety considerations, and data quality. A balanced inspection philosophy integrates both methods to optimize safety, reliability, and cost-effectiveness while complying with API and ASME requirements. Boiler inspections are subject to jurisdictional regulations that may vary by country, state, or local authority. Inspectors must be aware of legal requirements related to inspection frequency, inspector qualifications, documentation, and reporting. In many jurisdictions, ASME construction codes are legally mandated, while API 510 may be adopted for in-service inspection of non-jurisdictional or owner-user equipment. Understanding how regulatory rules interface with company standards and industry codes is essential to avoid compliance gaps. This section emphasizes the inspector's responsibility to verify applicable regulations before conducting inspections and to ensure that inspection outcomes meet both legal and technical expectations. API 510 defines the minimum requirements for in-service inspection, rating, repair, and alteration of pressure vessels, including certain boilers. For inspectors, this standard provides guidance on inspection intervals, thickness measurement, corrosion rate determination, remaining life assessment, and minimum thickness evaluation. API 510 also establishes qualification requirements for inspectors and emphasizes proper documentation. When applied to boilers, inspectors must carefully determine equipment eligibility and ensure consistency with jurisdictional rules. This section explains how API 510 principles are applied in boiler inspection programs and how inspectors should use the standard to support sound engineering judgments. API 572 serves as a companion document to API 510 by providing detailed guidance on inspection practices, damage mechanisms, and evaluation techniques. For boiler inspectors, API 572 offers practical advice on visual inspection methods, non-destructive examination options, and typical areas of concern. It also describes common forms of deterioration such as corrosion, erosion, cracking, and deformation. This guidance helps inspectors translate code requirements into effective field practices. By following API 572 recommendations, inspectors can improve consistency, accuracy, and completeness in both on-stream and off-stream boiler inspections. Although the ASME boiler and pressure vessel code primarily governs design and construction, it also provides valuable context for in-service inspection. Inspectors must understand original design conditions, allowable stresses, joint efficiencies, and material specifications when evaluating in-service damage. ASME Section 7 offers recommended guidelines for care and operation of boilers, which can inform inspection focus areas. Aligning inspection findings with ASME design intent ensures that assessments of fitness for service and repair acceptability are technically sound. This section highlights how ASME knowledge supports informed inspection decisions. Boilers are susceptible to a range of damage mechanisms due to high temperature, pressure, water chemistry, and combustion conditions. Common mechanisms include general corrosion, pitting, erosion, stress corrosion cracking, fatigue cracking, creep, and overheating damage. Inspectors must be able to recognize the conditions that promote each mechanism and identify visual or NDE indicators during inspections. Understanding damage mechanisms allows inspectors to target high-risk areas, select appropriate inspection techniques, and recommend suitable mitigation actions. This knowledge is fundamental to both on-stream monitoring and detailed off-stream examinations. Corrosion in boilers can occur on both fireside and waterside surfaces, each driven by different conditions. Fireside corrosion is often associated with fuel contaminants, sulfur compounds, and high-temperature oxidation, while waterside corrosion is influenced by water chemistry, oxygen ingress, and deposit formation. Inspectors must understand how operating practices and maintenance affect corrosion risk. Identifying corrosion patterns during inspection helps determine root causes and supports corrective actions such as water treatment improvements or operational changes. This section emphasizes the inspector's role in correlating inspection findings with process conditions. Cracking in boiler components may result from thermal fatigue, mechanical fatigue, stress corrosion cracking, or fabrication-related issues. Areas of stress concentration such as welds, nozzles, tube-to-tube sheet joints, and attachments are particularly susceptible. Inspectors must be trained to recognize surface indications of cracking and understand when advanced NDE methods are required. Early detection of cracking is critical to preventing leaks or catastrophic failures. This section explains common cracking mechanisms and inspection approaches relevant to boiler service. Creep damage occurs in boiler components operating at elevated temperatures for extended periods, leading to material deformation and eventual rupture. Overheating can accelerate creep and is often associated with poor heat transfer, deposits, or flow restrictions. Inspectors must be alert to signs such as bulging, distortion, or changes in material microstructure. Understanding operating temperature limits and material properties is essential for accurate assessment. This section outlines how inspectors identify and evaluate creep-related damage during inspections. The primary objective of on-stream inspection is to monitor boiler condition while maintaining operation. Inspectors focus on detecting active corrosion, leaks, abnormal vibrations, temperature excursions, and changes in operating parameters. On-stream inspections support early identification of deterioration trends and help verify the effectiveness of previous repairs or mitigation measures. While access is limited, on-stream inspection provides valuable real-time information that complements off-stream findings. This section clarifies the role of on-stream inspection within an overall integrity management strategy. Common on-stream inspection techniques include external visual inspection, temperature monitoring, infrared thermography, ultrasonic thickness measurements at accessible locations, and operational data review. Inspectors must ensure that measurements are taken safely and that data quality is sufficient for trend analysis. Selection of techniques depends on boiler design, operating conditions, and known damage mechanisms. Proper planning and coordination with operations personnel are essential to effective on-stream inspection execution. An on-stream visual inspection checklist helps inspectors systematically evaluate external boiler condition. Typical items include evidence of leakage, insulation damage, hot spots, corrosion at supports, condition of expansion joints, and integrity of safety devices. Inspectors should also observe abnormal noises, vibrations, or odors that may indicate internal issues. Using a structured checklist improves consistency and ensures that critical observations are not overlooked during routine inspections. On-stream non-destructive examination methods are limited by access and safety constraints but can still provide valuable information. Ultrasonic thickness measurements, acoustic emission monitoring, and infrared thermography are commonly used. Inspectors must understand method limitations, accuracy, and suitability for specific damage mechanisms. Proper interpretation of on-stream NDE results supports informed decisions regarding inspection intervals and the need for off-stream examination. Off-stream inspections are conducted during shutdowns and aim to provide a comprehensive assessment of boiler condition. Objectives include detailed internal visual examination, extensive thickness measurements, weld inspection, and evaluation of components not accessible during operation. Off-stream inspections allow inspectors to confirm damage mechanisms, quantify deterioration, and assess fitness for service. This section explains how off-stream inspections form the basis for long-term integrity planning. During off-stream inspections, inspectors can employ a wide range of techniques, including internal visual inspection, ultrasonic testing, magnetic particle testing, dye penetrant testing, and radiography where applicable. Proper surface preparation, access planning, and safety controls are essential. Technique selection should be based on anticipated damage mechanisms and inspection objectives. This section outlines best practices for executing thorough off-stream inspections. An off-stream visual inspection checklist supports systematic evaluation of internal boiler components. Items typically include condition of drums, tubes, tube sheets, weld seams, nozzles, refractory, and internals. Inspectors should document corrosion patterns, cracking, deposits, and deformation. A structured approach ensures comprehensive coverage and consistent documentation across inspection cycles. Off-stream inspections provide the opportunity for expanded NDE coverage to validate visual findings and quantify damage. Inspectors must plan NDE scope based on risk, prior inspection history, and known damage mechanisms. Coordination with qualified NDE personnel and clear acceptance criteria are critical. Effective NDE planning enhances inspection value and supports reliable integrity assessments. Boiler shells are primary pressure-retaining components and require careful inspection for corrosion, cracking, and deformation. Inspectors should focus on areas of high stress, such as longitudinal and circumferential welds, supports, and areas exposed to moisture. Thickness measurements and visual examination are key methods. Proper assessment of shell condition is essential for ensuring continued safe operation. Tubes and tube sheets are highly susceptible to corrosion, erosion, and overheating damage. Inspectors must examine tube ends, ligaments, and attachment welds for thinning or cracking. Sampling strategies are often used due to the large number of tubes. This section explains inspection priorities and evaluation considerations for these critical components. Headers and drums distribute fluid flow and are subject to thermal stresses and corrosion. Inspectors should evaluate internal surfaces, nozzle connections, and welds for signs of cracking or thinning. Proper access and cleaning are essential for effective inspection. Findings from these components often influence overall boiler integrity assessments. Welds and attachments are common locations for cracking due to stress concentration and metallurgical factors. Inspectors should apply appropriate NDE methods to evaluate weld integrity, particularly in high-temperature or cyclic service. Understanding original fabrication detail supports accurate interpretation of inspection results. This section emphasizes the importance of weld inspection in boiler safety. Refractory and insulation protect boiler components from excessive heat loss and overheating. Inspectors must assess their condition to identify hot spots, cracking, or material loss. Deteriorated refractory can lead to accelerated damage of pressure parts. This section outlines inspection considerations and common issues related to refractory systems. Thickness measurements are a core requirement under API 510 for assessing corrosion and remaining life. Inspectors must select representative measurement locations and ensure proper calibration of equipment. Trending of thickness data over time supports corrosion rate determination and inspection interval planning. Accurate measurements are essential for reliable integrity evaluations. Determining corrosion rates and remaining life is critical for managing boiler integrity. Inspectors use historical thickness data, operating conditions, and damage mechanisms to estimate future deterioration. These calculations support inspection interval decisions and repair planning. This section explains the inspector's role in developing and validating corrosion rate assessments. Minimum required thickness is established based on design conditions and code requirements. Inspectors must compare measured thickness to minimum allowable values to determine acceptability. API 510 provides guidance on these evaluations. Accurate minimum thickness assessment is essential for ensuring safe continued operation. When inspection findings exceed code limits, fitness for service assessments may be required. API 579 provides methodologies for evaluating flaws, thinning, and other damage. Inspectors play a key role in identifying when FFS assessments are needed and providing accurate input data. This section highlights the relationship between inspection and FFS evaluation. Inspection planning involves defining scope, methods, and frequency based on risk and code requirements. API 510 establishes baseline intervals, which may be adjusted based on inspection results and corrosion rates. Inspectors contribute by providing accurate condition data and recommendations. Effective planning supports safe and economical operation. Risk-based inspection integrates probability and consequence of failure to prioritize inspection resources. Inspectors support RBI by identifying damage mechanisms and providing reliable inspection data. RBI can optimize inspection intervals and focus attention on high-risk components. This section explains how inspectors contribute to RBI programs. Accurate documentation is essential for regulatory compliance and integrity management. Inspection reports should clearly describe findings, measurements, locations, and recommendations. API 510 emphasizes proper record-keeping. This section outlines best practices for inspection documentation and communication. Inspectors frequently encounter findings such as localized corrosion, tube thinning, cracking at welds, and refractory damage. Understanding common issues helps inspectors quickly recognize abnormal conditions. This section summarizes typical findings and their implications for boiler integrity. Safety is paramount during both on-stream and off-stream inspections. Inspectors must follow site safety procedures, including lockout/tagout, confined space entry, and personal protective equipment requirements. Hazard awareness reduces the risk of injury. This section reinforces key safety considerations for inspectors. API 510 specifies qualification requirements for inspectors, including experience and examination. Competency also requires ongoing training and familiarity with boiler operation and damage mechanisms. Qualified inspectors are critical to reliable inspection outcomes. This section emphasizes professional responsibility and competence. Proper shutdown preparation is essential for effective off-stream inspection. Activities include cleaning, ventilation, access installation, and safety isolation. Inspectors should coordinate with operations and maintenance teams. Good preparation improves inspection quality and efficiency. The inspection process concludes with clear recommendations and defined follow-up actions. These may include repairs, monitoring, operational changes, or revised inspection intervals. Inspectors must communicate findings effectively to stakeholders. This final section reinforces the inspector's role in supporting safe, reliable boiler operation through informed decision-making.